Good morning, everybody. During the last lecture, we have seen collisions, elastic collisions, inelastic collisions, and completely inelastic collisions. We have discussed the difference between this type of collisions, and today we will learn a little bit more information about elastic collisions, and we will discuss different situations in elastic collisions. Here we have very nice example with billiard balls. So here you see many billiard balls and they collide. What happens during this collision? Let's consider that this is elastic collision. So how to keep their kinetic energies before the collision and after the collision. So how to conserve the kinetic energy. So billiard balls deform very little when they collide. You can consider like a spring. Let me draw. During the last lecture, we have discussed this type of system with two boxes and there are springs in front of them. Okay, so during the collision, these springs are compressed and kinetic energy is stored as a potential energy in the springs. Then after the collision, the potential energies stored in the springs again converted to the kinetic energy, and then kinetic energy is conserved. Okay, so here what will happen if you have two billiard balls and they collide? So what happens? They deform a little bit during the collision, okay? Some deformation is produced here, but this can be repaired, let's say, like springs, okay? So the force of interaction between the balls is almost perfectly conservative and the collision is almost perfectly elastic, okay? So at the beginning, during the collision, some parts of the kinetic energy is stored as potential energy here on the balls, okay, due to the deformation on the balls. And then this deformation is repaired, and then this stored potential energy again converted to the kinetic energy, and kinetic energy is conserved. So this is the example for elastic collisions. But what we see here, we have many particles, many objects, many balls, okay? So they collide each other. So during this lecture, we will discuss different situations of elastic collisions. So look at this one. Here we have an example for the elastic collision. Here we have an A object on the left side, and here we have a B object, and this A object has certain VA1 initial velocity before the collision. So this part is before the collision, this is during the collision, and this last part is after the collision. So after the collision, this particle moves back with some certain velocity, and this B object is moving to the right side with some certain B velocity. Let's consider that this collision happens in certain axis, okay? And let's consider that it happens in one dimension, okay? So it means that the velocity of A and velocity of B lie along the same line. So then we can apply conservation of energy and conservation of momentum. How can we apply conservation of momentum? If the net force acting on the system is zero, then momentum is conserved. Momentum does not change because the net force is given with dp over dt, okay? If the momentum is constant, if it does not change by time, then derivative is zero. Then it means that net force acting on a system is zero. Here, let's consider these balls are staying on certain table, okay? So this has certain weight, this has certain weight, and there's a normal force acting on A, there's a normal force acting on B, but these forces are equal to each other, and net force along the y-axis is 0. And in addition to that, let's consider there is no friction on the surface. Then along the x-axis, there is also no net force. Then net force acting on the system is 0. Then momentum is constant, momentum is conserved, okay? So for this condition, I can apply conservation of kinetic energy and conservation of momentum. So just use these two conservations. First of all, let me delete this part and clean the board. Then you can better see the velocities before the collision and after the collision. So look at this one. Here we have conservation of kinetic energy. This is the initial kinetic energy of the A ball. This is the initial kinetic energy of the B ball. This is the before the collision. To the left side we have, and on the right side we have total kinetic energy after the collision. The final kinetic energy of the A ball and the final kinetic energy of the B ball, okay? We can write this expression by using conservation of kinetic energy. So what about the conservation of momentum? Conservation of momentum can give us this expression: initial momentum of the A ball plus initial momentum of the B ball are equal to final momentum of the A ball, final momentum of the B ball. So if you consider that this is the initial momentum of the system, which is equal to the final total momentum of the system, we can write this expression because momentum is conserved, momentum is constant during this collision. Okay, then let me continue and discuss special conditions in elastic collision. So what about if body B is at rest before the collision? Here we have again two balls. This is the A ball on the left side. It has certain velocity and it is moving along the positive X direction, let's say. And here we have a B ball. B ball is at rest. This is a special condition, particular case, and the velocity of the ball is 0. B ball is 0. Okay, now what will happen if the collision is elastic here? Then let's try to write the kinetic energies. Write the conservation of kinetic energy. This first equation is the conservation of the kinetic energy. Here we have kinetic energy of the A ball on the left side. What about the kinetic energy of the B ball? It is 0 because it is staying at rest at the beginning. So there is no kinetic energy from the B ball. So before the collision, we have only kinetic energy from the A ball. After the collision, we have final kinetic energy of the A ball and final kinetic energy of the B ball. What about the momentum conservation in this second equation? So initial momentum of the A ball plus initial momentum of the B ball. Since the velocity of the B ball is 0 at the beginning, then there is no contribution to the momentum. In this equation, we have only momentum from the A ball. Then after the collision, we have momentum from both A and B balls. Okay? So here we have two equations. By using these two equations, you can get expression for the velocity of the initial velocity of the A ball, or you can get the expression for the final velocity of the B ball, or you can get the expression for the final velocity of the A ball, okay, by using these two equations. So just rearrange these two equations, okay, just rearrange them. Here we have 1/2, 1/2, 1/2. You can cancel these ones, okay? Then you can write this first expression like this. Here we have this one. Just keep this one here and move this one here to the left side. And finally, we have this expression. Okay, we have just rearranged the first equation comes from the conservation of kinetic energy. We have just rearranged this one. Okay, rearrange this one. So now here we have VA initial square minus VA final square. I can write this expression from the mathematics you will remember like this. Okay, this expression can also be written in this form you remember from the mathematics. Okay, if you multiply this one with this one, you will get finally this expression here. So what about this expression here? Here we have again the final momentum of the B ball on the right side. Just keep this one on the right side and take this one to the left. So finally we have here final momentum of the B ball, and it can be written with MA times VA initial minus VA final. What do you see here? We have MA, and here we have this expression. Let me change the color of the pen, then I will show you. What do you see here? This one is equal to this one, right? So instead of this one, you can use MB/VB/2x. Okay, just take this expression, put it there, and then you can get a solution for the final velocity of the B ball. So this is the final velocity of the B ball. It depends on the initial velocity of the A ball plus the final velocity of the A ball. Okay. So now I have expression about the final velocity of the B ball. What was the initial velocity of the B ball? B ball was at rest at the beginning, and some part of the kinetic energy is transferred to the B ball. Now finally we have velocity of the B ball, and B ball has certain kinetic energy and momentum after the collision. So let me continue. Look at this expression. We have final velocity of the B ball, initial velocity of the A ball, final velocity of the A ball. But I would like to calculate final velocity of the B ball and final velocity of the A ball after the collision independently. So how to get these two velocities? So if I take this one and use in these equations, then I can get this expression MB initial velocity of times initial velocity of the A and plus final velocity of the A. Then this will be equal to MA times initial velocity of the A ball minus final velocity of the A ball. And then I can get this expression for the final velocity of the A ball. What do you see here? This final velocity of the A ball depends on the initial velocity and mass of the A ball and mass of the B ball. Okay, now I have expression for the final velocity of the A ball. What about the final velocity of the B ball? From this expression, you can also get this term, final velocity of the B ball. It depends on the mass of the A ball, and it depends on the mass of the B ball, and it depends on the initial velocity of the A ball. So now we have two expressions for the final velocities of the balls. Okay. So just keep these two equations in your mind, okay? Final velocities of the balls after the collision. Then we will use these two equations for different cases, for different situations in the following transparencies. So let me discuss this one. Here we have two balls again. This is the A ball, this is the B ball, but this B is very large, very massive. It has huge mass, okay? Mass of MB is much bigger than mass of A ball, okay? Then this is very small. You can ignore its mass, okay, in some conditions. So now this is the before the collision. B ball is at rest. So VB1X is 0. Okay. And here we have A ball with some certain mass, which is very small compared to the mass of the B ball, and it has certain velocity. And B is at rest. So what will happen? After the collision, you can calculate the velocities of two balls by using these two equations. Okay, in the previous transparency, we have calculated final velocities of the balls in elastic collision if the B ball is at rest. Now I will apply these two equations to this example. Let's try to calculate the final velocity of the A ball. Let me change the color of the pen, and then I will continue. So, what do you see here? Here we have MA, here we have MB, and I have given this information at the beginning. This MB is much bigger than MA. Then this term here will be minus MB. Okay, and here we have MA plus MB. So since this MA is very small compared to the MB, you can ignore this one, and this can be written as MB. So the result is minus MB over plus MB VA1X. So this cancels this one. Okay, so finally, final velocity of the A ball is given with this expression minus A1X. If the mass of the A ball is very small compared to the mass of the B ball, okay? What do you see here? This A ball goes back after the collision with more or less the same velocity, okay? So here we have minus sign in order to show the opposite direction. What about the final velocity of the B ball? At the beginning, B ball was at rest. Now just apply this equation and try to solve it. Here I have MA, you see, mass of the A ball. And here I have mass of the A ball plus mass of the B ball. Since MB is much bigger than the MA, this term can be written like this, okay? And now I have this expression for the final velocity. 2MA over MB times VA1X, okay? So this is huge compared to this one. Then this term is very small, okay? Then the final velocity of the B ball is much smaller than the initial velocity of the A ball, okay? So you can transfer some parts of the kinetic energy of the A ball to the B ball, and it has certain velocity, but this velocity is very small due to this relation. So then B hardly moves, okay? Any question here? Do you have any question? Then let me continue with another condition. let's consider that B ball is much less massive than the A ball. Now A ball has certain velocity and its mass is much bigger than the mass of the B ball. And what do you see here? B ball is at rest. So B1x is 0. Okay. Now let's apply these two equations for this example. So what will happen to the final velocities of the balls after the elastic collision? So look at this expression. This MA is much bigger than MB, then this part of the equation will be MA, okay? And this MA here is much bigger than the MB, then this part will also be roughly equal to MA. MA will cancel this MA, and then finally what we'll have? Finally, we will have this one. The final velocity of the A ball will be roughly about the initial velocity of the A ball. Okay? And what about the final velocity of the B ball? Just put here again this assumption, MA is much bigger than the MB. Then here I have MA, and instead of this one, since this MA is much bigger than MB, I can just write this one roughly MA. So then this equation will be like this: 2MA over MA times VA1x. Okay, so this MA will cancel this one, and then this final velocity of the B ball will be roughly 2 times bigger than the initial velocity of the A ball. Okay, so if B is much less massive than B, then A slows a little bit, okay? So you can ignore its slowing, okay, because its initial velocity is more or less equal to its final velocity. But during this time, after the collision, B picks up a velocity of about twice the original velocity of the A, okay? So this comes from the equations of the final velocities, which we have calculated in the previous transparencies. Now let me discuss the final condition. In this final condition, A ball and B ball have similar masses, okay? You can consider that MA is more or less equal to the MB, okay? And we have certain velocity of the A ball before the collision, and before the collision, B ball is at rest, okay? It has no velocity. Then what about the velocities after the collision? So here we have MA minus MB. This will give us 0. Since MA is more or less equal to the MB, this will be 0. Then the final velocity of the A ball after the collision will be 0, according to this relation with this condition. And let's apply this condition for the B ball. Here we have 2MA, here we have MA plus MB. Then this can be written like this, 2MA, because this MA is more or less equal to the MB. Then I can write it like this, 2MA, 2MA here, 2MA here. Then the final velocity of the B ball is equal to the initial velocity of the A ball. So before the collision, B was at rest, but after the collision, A ball is at rest, okay? All the kinetic energy is transferred to the B ball. So this is happened This has happened in billiard, okay? So if you play with billiard balls, so maybe you observe this type of behavior many times. Any question until this point? Then let me continue. Here in this part of my lecture, we got this expression, okay? This one. Final velocity of the B ball is equal to initial velocity of the A ball plus final velocity of the A ball. Just use this expression here, okay? This expression, and just keep this one here and just move this one to the left side. So finally, here I have initial velocity of the A ball on the left, and on the right side, I have final velocity of the B ball minus final velocity of the A ball. What do you see here? So let me show you here. This is the A ball, this is the B ball, and this is the final velocity of the A ball. This is the final velocity of the B ball. Look at the picture. So here we have final velocity of the B ball minus final velocity of the A ball. What is this? We have learned relative velocity, okay? So this is the relative velocity of B to A, or the velocity of B ball relative to A ball after the collision, okay? So this expression here on the right side gives us the velocity of the B relative to A. And this is the negative of the velocity of B relative to A before the collision. So look at this one. Before the collision, we have VB1, which is 0, okay? Or it can move with some certain velocity along the negative x, let's say this is VB1. Then what about the relative velocity of B here? The velocity of B relative to velocity of A before the collision, okay? And this is the velocity of B relative to A after the collision. So here, what I have told you that this expression here is the negative of the velocity of B relative to A before the collision. So now listen carefully. The relative velocity of B to the A before the collision is equal to the relative velocity of B to A after the collision in magnitude, but with different direction, okay, with opposite sign. So then we will use this information here. In a straight line elastic collision of two bodies, two balls, the relative velocities before and after the collision. Relative velocities before and after the collision have the same magnitude but opposite sign. Okay, what do you see here? This is on the left side, we have relative velocity of B to A after the collision. On the right side here, within this bracket, we have relative velocity of B to A before the collision. In magnitude, they are same, but there is a negative sign here. Okay, so this result provides an alternative and equivalent definition of an elastic collision and very helpful in some problems. In an elastic collision, the relative velocity of two bodies has the same magnitude before and after the collision. Don't forget this one. So what do you see here? If the relative velocities are the same before and after the collision, then you can consider that the total kinetic energy is conserved. Indeed, in elastic collisions, total kinetic energy before the collision and after the collision is same. So now let me continue with this example from the book, example 8.10, an elastic straight line collision. Actually, we have discussed this example in example 8.5 in the previous lecture. What we have here, we have two masses. This is the A box and this is the B box. This has certain mass 0.5 kilogram. This has certain mass 0.3 kilogram. And before the collision, this A box has certain velocity, 2 meters per second, and B box has opposite velocity with same magnitude, minus 2 meters per second. And what is the question? What are the final velocities of the gliders or final velocities of the boxes, objects? Okay, you just consider that there is no friction between the boxes, objects, and surface. So here, compared to this example, now we have springs. Okay, here we have springs. So there is no friction. Here we have springs. Then you can consider that the kinetic energy is conserved and also momentum is conserved. At what conditions momentum is conserved? If there is no external force acting on this system, momentum is conserved. Okay? If there is no force acting on this system, then momentum is constant. Okay? Momentum is conserved. So here, there is a weight acting on this box. There is normal force, but the net force along the y is 0. Again here, net force along the y is 0. And there is no friction on the surface. So there is no net force along the x-axis. So then the net force, net external force acting on this system is 0. Then momentum is conserved. Don't forget this information. And kinetic energy is also conserved. How it is conserved? Before the collision, here we have spring and here we also have spring. This has certain kinetic energy. This has certain kinetic energy. And during the collision, these springs are compressed and kinetic energies are stored as potential energies in the springs. Then after the collision, this potential energy again converted to the kinetic energy, and then kinetic energy is conserved. So this relation between kinetic energy and potential energy and the conservation of total mechanical energy, we have discussed all these things in the previous lectures. I will not go into detail here. So let me try to solve this example. What we have said, the momentum is conserved and this is the elastic collision and kinetic energy is conserved. So just try to write also this relation, what we have learned here. This is very important for many applications, as I told you. So I can also use this expression here. What I have told you that the relative velocities after the collision is equal to the negative sign of the relative velocities before the collision. So I can also use this expression here in order to calculate the final velocities. So this is the relation between elastic collision and relative velocities. This is the relative velocities before the collision. This is after the collision. And I know the velocities before the collision because they are given in the question. Okay, just put them here. So velocity of B relative to A is given with 4 meters per second. And by using the conservation of momentum, you can also get this expression or use this expression, initial momentum of the A object plus initial momentum of the B object equal to final momentum of the A object plus final momentum of the B object. Okay, so I know the mass of A, I know the initial velocity of A, I know the mass of B, I know the initial velocity of the B, but what we have here, look at carefully, here we have a negative sign because the direction of the B at the beginning is opposite, okay? Don't forget negative sign here. Then on the right side, after the collision, this is the total momentum of the system. I don't know of this final velocities, just keep them here. Then I have another expression. Now I have two expressions. The first one is this one, which is equal to 4 meters per second. And the second one is this one, 0.5 final velocity of A and 0.3 final velocity of B. And the sum of them is equal to 0.4 meters per second. So by using these two equations, you can get this results for the final velocities of A and B. What do you see here? The final velocity of A is given with negative sign because after the collision, this A object is moving along the negative x direction. So the magnitude is 1 meter per second. And what about the velocity of this one? 3 meters per second. At the beginning, this was moving along the negative x direction, this negative sign here, but now it is moving to the positive side. Okay. So here there is a caution. Be careful with the elastic collision equations. So you could not have solved this problem by using equations 824 and 825. What was these equations? We have used these equations here. Look at these equations. You cannot use these equations here. You cannot use these equations. Why? During calculation of these equations, this 824 and 825, we have considered that B is at rest at the beginning, and we have considered VB1x is 0. Initial velocity of B is 0. We have considered that B is at rest at the beginning. But within this problem here, within this example, B is not at rest. B has certain velocity before the collision. Okay, then you cannot use these equations. Okay, you must be very careful with the questions. Then let me continue with another example concerning the elastic collision. This is the example from real application in nuclear reactors, moderating fission neutrons in a nuclear reactor. The fission of uranium nuclei in a nuclear reactor produces high-speed neutrons. Before such neutrons can efficiently cause additional fissions, they must be slowed down by collisions with nuclei in the moderator of the reactor. Let me show you. Let's consider that here you have one neutron and then it has certain velocity, let's say, and here there's a huge, okay, let's consider this is huge compared to this one. This is the uranium, okay, uranium atom, uranium nuclei, let's say, and then after the interaction of this energetic neutron and uranium, as much as I remember, 2 or 3 neutrons are produced, okay? So these neutrons are also very energetic and also energy is produced, okay, plus energy, okay? So this is used in nuclear reactors and also in nuclear weapons and also nuclear reactors in submarines and also aircraft carriers in the armies. So very important for technological and defense applications and also for energy applications. Okay, so here we have very energetic neutrons, or here we have very energetic neutrons. Before the interaction with the neutron and uranium atom, here you have to use, let's say, a barrier, okay, to slow down these neutrons, okay? So what is this barrier or moderator? This is called as moderator, okay? It moderates the velocities, initial velocities of the neutrons. The first nuclear reactor built in 1942 at the University of Chicago used carbon graphite as the moderator. Here you use carbon atoms, okay, many carbon atoms, and these neutrons will collide with carbon atoms and they will lose some parts of their initial energies, initial velocities. Suppose a neutron traveling at 2.6 times 10 to 7 meters per second undergoes a head-on elastic collision with a carbon nucleus at rest. So let's consider here there is a carbon atom before the uranium, okay? And the mass of the neutron is 1U. This is the atomic mass unit and equal to 1.66 times 10 to minus 27 kilogram, okay? The mass of the neutron is 1U and small u. The mass of the carbon nucleus is initially at rest. Neutron has certain velocity, but the carbon is 0 at the beginning, okay? So neglecting external forces during the collision, find the velocities after the collision. So after the collision, what is the velocity of the neutron and what is the velocity of the carbon atom here? Here we have important term, undergoes a head-on elastic collision. So what we have here, this carbon atom, here we have neutron, let's say at the beginning, it has certain initial velocity, and here we have huge carbon atom compared to the neutron, and it is at rest. Carbon atom is at rest at the beginning. So then I can apply these rules which we have learned in the previous transparencies. In an elastic collision, if the B particle is at rest before the collision, and if the interaction is elastic, I can apply this for the final velocity of the neutron and final velocity of the carbon atom. I can apply these rules. Then just use these rules. Mass of the neutron is given, mass of the carbon atom is given, and velocity of the neutron is given, and then you can calculate the final velocities. Okay. Last question, two-dimensional elastic collision. Up to now, we have discussed the collisions in one dimension. But what happens if the collision is formed in two dimensions? Here we have an example. Figure shows an elastic collision of two pucks, masses MA and MB, on a frictionless air hockey table. Okay, here we have a table and we have two pucks. This B at rest at the beginning, this A has certain velocity. Okay, this is the position of the A, this is the position of the B. And after the collision, A goes in this direction with this velocity, with this angle, alpha, and B goes in this direction with this beta angle. And what about the velocity of the B? Find the speed of B atom or B puck after the collision and find the alpha and beta angles. So what about the conservation of kinetic energy and what about the conservation of momentum? The surface is frictionless then the net force acting on this system along the x-axis is 0. Also along the y is 0. Let's consider that this x and y both are located on a horizontal surface, okay? And along the z-axis, there is a normal force and weight. So just consider like this. Let's consider this is positive z, this is negative z, and this is x, positive x, and this is positive y, let's say, okay? And now we are looking from top. So then the collision happens here in this horizontal plane, and let's consider here we have a hockey puck, and there's a normal force, there's a weight. Since this normal force and weight are equal to each other, and the net force along the z-axis is also 0. So if the net force is 0, then momentum is conserved. Okay, you can apply conservation of momentum. You can also apply conservation of kinetic energy. Why? Because the collision is elastic. Okay, in elastic collision, we have discussed during the last lecture, kinetic energy is conserved. So just apply conservation of kinetic energy, initial kinetic energy of the A ball, final kinetic energy of the A puck, final kinetic energy of the B puck. And this is the final velocity of the B puck. But this is the magnitude. What about its direction? What about the beta angle? Okay. So in order to calculate this one, we have to continue, then apply conservation of the momentum. But in this case, you must be very careful. Before the collision, we have movement only in this direction along the positive x. Okay, so you can consider only momentum along the x-axis. But after the collision, what happens? Look at the A object. Look at the B object. So after the collision, this A object has momentum along the y-axis and momentum along the x-axis. And this B object has momentum along the y-axis, along the x-axis. So you have to write conservation of momentum for both x and y components of the total momentum. Let me start with the momentum conservation for the x component of the momentums. Before the collision, along the x-axis, this has some certain momentum, okay? And this has 0 momentum because it is at rest, okay, along the x-axis. So I can write this one. Initial momentum of the A puck is equal to final momentum of the A puck plus final momentum of the B puck. Then I can get this expression. Here I have the initial momentum of the A puck. What about the final momentum of the A puck, but along the x? Along the x, you have to take velocity times cosine alpha times mass. So here we have mass. Here we have, instead of Vx after the collision, we have cosine alpha. And for the B puck, we have again velocity of the B after the collision times cosine beta. Then we have this expression. What about the momentum conservation along the y-axis? Before the collision, look at this picture here, this figure. Before the collision, we don't have any momentum along the y-axis. For this reason, before the collision, momentum, total momentum along the y-axis is 0. After the collision, we have momentum components from both A and B hockey pucks. Okay, then I can write them with sinus alpha and sinus beta. Then Here I have cosine beta, here I have cosine alpha, here I have sinus alpha, sinus beta, and if you use these two equations, and also if you use information here, then you can calculate alpha and beta angles. You will use this expression sinus square beta plus cosine square beta will give us 1. Okay, if you apply this rule from the geometry, from the mathematics, then you can calculate this alpha and beta. This is the solution of this problem, a two-dimensional elastic collision. So what we have done, the very important or the most important thing here is that before the collision, momentum is only along the x-axis. But after the collision, we have momentum both along the x and y axis. So we have x and y components of momentums after the collision. Remember the momentum. Momentum is a vector. It has certain direction. Okay, we didn't do this one for the kinetic energy. For the kinetic energy, we did not consider the conservation along the x-axis, conservation along the y-axis, because kinetic energy is not a vector. Kinetic energy is a scalar, independent from the direction. Okay, we have just written the initial total kinetic energy is equal to final kinetic energy. But in case of conservation of momentum, you have to consider x and y components of the total momentum. Don't forget. Any question here? Okay, let me continue with the center of mass for very complicated systems and also for the extended systems. If you have several particles with different mass and different velocities, then center of mass information is very useful. So let's consider we have mass of m1 and we have mass of m2, like this one here. Look at this one. This is mass of m1, mass of m2, m3, m5, m4. Okay, we have many masses here. Each of them has certain velocities, but this system has certain center of mass. Okay, so since it is not so easy to deal each part of this system individually, then instead of this one, I will use the term center of mass, and I will use the position of the center of mass. I will use the velocity of the center of mass. I will use the momentum of the center of mass. So now let's calculate the center of mass of the system for the x coordinate. Here we have mass 1 and the position of the mass 1 plus mass 2 times position of the mass 2 plus m3 times position, x position of the mass 3 divided by mass of the system, m1 plus m2 plus m3. Okay, what we have here, you can write this one like this. This I defines the number of the mass, which mass you are talking about, mass ith times position of the mass ith. So here we have the total mass. So I can also calculate the y coordinate of the center of mass by using this expression. So finally, if you would like to find the position vector of center of mass of a system of particles, then you can write this expression. Look at here, we have m1 x1, m1 y1, but instead of x and y components, I just use the position vector of individual particles here, m1 times r1 plus m2 times r2 plus m3 times r3 divided by total mass, masses of individual particles. This is the position vector of center of mass. Let me draw what I mean. Here we have coordinate system, x-axis, y-axis, and here we have many masses with different positions. This has different position On y and x-axis, this has different positions. On y and x-axis, this has different positions on y and x-axis, but the center of mass of this particle 7 with this one. This is the position vector r. Okay, this is the position vector for the center of mass of the several particles, which we have learned here. Okay, here let me tell you some useful information concerning the center of mass of symmetrical objects. Be careful, objects must be symmetrical in this discussion. Let's consider here we have a cube, and here we have a sphere, here we have a cylindrical object, okay? And let's consider that all these objects are homogeneous. Don't forget this one, okay? If these objects are homogeneous, and then the center of mass of the symmetrical objects is the geometric center. Geometric center of cube, geometric center of sphere, geometric center of the cylinder. When, if the objects are symmetrical and if the objects are homogeneous, okay? So here we have another conditions. If you have a disk like this, and if this is the axis of symmetry, and here we have a donut. If an object has an axis of symmetry, the center of mass lies along it. So center of mass is here on the axis of symmetry. As in the case of donut, the center of mass may not be within the object. Look at this one, center of mass here. Okay, this is not within the object. Center of mass is here. So be careful with these things. And then let me continue with the example of center of mass. Center of mass of a water molecule. Here we have a water molecule. Water molecule is given with this one, H2O. So we have 2 hydrogen atoms and we have 1 oxygen atom. Okay, so you know from the chemistry. So figure shows a simple model of a water molecule. The oxygen-hydrogen separation is D, 9.57 times 10 to 11 meter. It is more or less around 1 angstrom, okay, something like this. The distance between the center of the hydrogen and center of the oxygen, and here again we have the same distance. Each hydrogen atom has mass 1U. So what is hydrogen atom? Hydrogen atom contains 1 proton in the nuclei, right? 1 proton in the nuclei, and also 1 electron is traveling around this nuclei. And the mass of this 1 proton is given with 1U, atomic mass unit, and the oxygen atom has mass 16U. Why? Because within the oxygen atom we have 8 neutrons and 8 protons. Okay, so this has 8U, this has 8U, and in total 16U. Find the position of the center of the mass. So this is the center of mass of the hydrogen atom, this is the center of mass of the hydrogen atom, and this is the center of mass of the oxygen atom. What about the center of mass of this system? So here we have an angle between the axis of 2 hydrogen atoms. So then the oxygen atom is at x is equal to 0, y is equal to 0. We are talking about center of mass. So the position of the oxygen, I choose x is 0, y is 0, okay? And I am calculating the position of the hydrogen atom here, x hydrogen, and it is given with d times cosine this angle here, okay? and y coordinates, this one, okay? So in order to calculate the y coordinates, you can use the sinus angle. And here we have positive and minus. Here we have positive, here we have minus, okay? Then what about the center of mass of this system? For the x coordinate, just write the mass of the hydrogen atom and the x position of the hydrogen atom, mass of the hydrogen atom, x position of the hydrogen atom, and mass of the oxygen and the x position of the oxygen over total mass of the system, mass of the hydrogen, mass of the hydrogen, mass of the oxygen, and then we have found the x position of the center of mass. What about the y position of the center of mass? Just put all information into the equation, then you will get 0. So then D is given. What is D? D is given here, the distance between the hydrogen and oxygen atoms. Just put this D here within this equation here, and then you can calculate center of mass of this hydrogen molecule, which is given 6.5 10 to minus 12 meter. What do you see? This is very small number. Here I have minus 12 power of minus 12. So then this is very small number. Then look at this one. Let me clean this picture and you will better see it. Look at this picture. The center of mass is shown with this arrow, and center of mass is somewhere here, which is very close to the origin, very close to the center of mass of the oxygen. Why? Because oxygen is very heavy, okay? Mass of the oxygen is huge compared to the mass of the hydrogen atoms here in the water molecule. Any question here? Then let me continue with the motion of the center of mass. Here I have given the x position. If I take time derivative of x, center of mass, then I can get x center of mass. If I take time derivative of the center of mass, then I can get y center of mass, y velocity of the center of mass, okay? Just do that. Then we have velocity of the center of mass along the x-axis, velocity of the center of mass along the y-axis. Then we have this expression: individual mass of the particles, individual velocities of the particles, but in total they have certain velocity, okay? This is the velocity of center of mass. And I can also write this direction with a single vector equation. The velocity of the center of mass is given with the velocity of the first particle times mass of the first particle, and mass of individual particles and velocity of the individual particles divided by the total mass. And instead of total mass, I can use this mass, capital M, okay? Then if you multiply this one, then I have here mass times total mass of the system times velocity of center of mass. Then here we have m1 v1 here plus m2 v2 plus it goes. What about m times v? M times v is total momentum of the system, okay? Now I have relation for the total momentum of the system and velocity of center of mass. Okay, let's continue with the motion of center of mass. Here you see a range. Look at the picture here. We have a range. Here we have a table, and we have a range on the table. This is the, let's say, center of mass of the range, and this is the table. Then you throw this table in this direction, and you are watching from the top, okay? You are watching from the top and you are taking the picture from the top. So what about the forces acting on this range? Let's consider that this surface is frictionless and there is no force, net force, acting on this range along the x-axis, and there is no force acting on this range along the y-axis. Let's consider this is the x, this is the y, and what about the z-axis? Z-axis. Along the z-axis, we have weight and normal force. Since they are equal to each other, then the net force along the z-axis is also 0. Okay, then the total force acting on a system is 0. Then the change in the momentum of the system is 0. Then momentum is conserved. Okay, so then what about the velocity of the center of mass? We have discussed that velocity of center of mass times total mass of the system is given with this expression. It is equal to the momentum. So here, then let's come to this example. The net external force on this range is almost 0, we have already discussed, as it spins on a smooth horizontal surface seen from above, we have discussed here. Hence, the center of mass moves in a straight line with nearly constant velocity. So what you see here, the center of mass moves with nearly constant velocity. Why velocity is constant? Why velocity is constant? Because net force is 0, then momentum is conserved, then momentum is constant. If the momentum is constant, then the velocity is constant, okay? Velocity does not change. Here, then, let me continue with the external forces and center of mass. Be careful with this part. Up to now, I have considered that external forces are 0. I have considered that there is no external force acting on the system. But what happens if the external force is not 0? Okay, then what will happen? Here we have this expression, mv center of mass is equal to this expression, or equal to momentum, total momentum of the system. If I take time derivative of this one, v center of mass over dt, then what is this? This is the acceleration of the center of mass. Just use this information and then I can get this expression. This is the mass, total mass of the system. This is the acceleration of the center of mass. So what about this one? If you take time derivative of this momentum here, let me do it like this. It is much better to understand. With this method, it looks very dirty. Then I will use better representation here. So we have this information, and I take time derivative of this one. Time derivative of the center of mass, time derivative of momentum. Okay, just take time derivative of this one. So mass is constant. If mass is constant, you can write it like this: center of mass over dt. And on the right side, we have time derivative of momentum. And this is acceleration of center of mass. What about this? This is the net force acting on the system, right? The change in the momentum. Then I can write this expression like this: m times center of mass is equal to net force acting on the system. Okay, So what about this net force? Net force includes both external forces acting on a system and internal forces the particles within the system applies on each other, okay? This is the sum of all forces on all particles, okay, which is given with m times a center of mass. And what about the internal forces, total internal forces? In the previous lecture, we have discussed isolated systems. In isolated systems, due to the Newton's third law, all the internal forces cancel in pairs. Then this is zero. Okay, remember the two astronauts, okay? So they touch each other. So this applies a force on this, this applies a force on this. These forces are equal to each other. Both of them are internal forces, but they have opposite signs. Since it is in positive direction, since it is in negative direction, and since they are equal in magnitude, then the net internal force is zero because they cancel each other. So then I can write this one. Here I have external force, and the net external force on a body or collection of particles is given with total mass of the body or collection of particles, then the acceleration of the center of mass. Any question here? Just apply this information here, external forces and center of mass. Remember this formula, keep this formula here, external forces equal to mass of the center of mass and total mass of the system and acceleration of the center of mass. So here we have a rocket. It has certain mass, okay? And what about the external forces acting on this one? Let's ignore a resistance, okay? Then what about forces acting on this one? There is weight, okay, due to gravity, no other forces. So net force, net external force is given with this weight. This is the mass of the system. Here we have acceleration. What is acceleration here? Acceleration is g if only weight is acting on this one, okay, gravity. So then let's consider that at this point, this missile or this shell explodes, okay? Then this part is moving in this direction with this trajectory, and this part is moving with this trajectory, okay? This also happens in rockets, okay? So then what about their trajectories? What about the trajectory of the center of mass? Look at this one. If this does not explode, this will follow this center of mass, the trajectory of the center of mass, okay? This one. But whenever this shell explodes, this part is moving with this trajectory, this part is moving with this trajectory, but what about the center of these two particles? What about the center of mass of these two particles? What about the center of mass of these two particles? So even after explosion, they follow the trajectory of the center of mass, okay? Don't forget. Then let me finish with this one, the center of mass and external forces. I have already shown you this expression, the total net external force acting on a system is given with the change in the momentum of the system, okay? But if the net force, net external force is zero, then the total momentum is constant. If this is zero, then the derivation is zero. There is no change in the momentum. Momentum is constant, and then momentum is conserved if external force is zero, net external force is zero. We have already discussed all these things, but just to remind you, then let me finish the center of mass with this application, very important for astronomy, for, let's say, space applications, finding planets beyond our solar system. Planets orbiting distant stars are so faint that they cannot be seen with even the best telescopes. But they can be detected by using the idea that a planet and its parent star orbit around their common center of mass. If we observe a star wobbling around a point, we can infer that there is an unseen companion planet and can actually determine the planet's mass. So hundreds of planets around distant stars have been discovered in this way by using the center of mass phenomenon. Any question here? Okay, I will finish this chapter with rocket propulsion, very important for technological applications and also for defense applications. For example, you will send a satellite to the space, to the certain orbit, you have to use rockets. For example, you have to send some materials and equipment to the International Space Station in the space, then you have to use rockets. For example, you have to send people, astronauts, to the International Space Station, then you have to use rockets. For example, you would like to save yourself from the missiles and bombs of the enemies, then you have to produce missiles defense system, okay? Missile-based defense system, then you have to use rockets. So this information is very important for our daily life, for many applications. So without these rockets, you cannot carry satellites into the space, and you cannot get very fast internet. You cannot get very good pictures of the Earth's places by using the maps, okay? So all these things be realized by using the rockets. And what is the working principle of the rockets? What is the rocket propulsion? During this lecture, we will learn all the things. So in the Newton's second law, we have used this rule, F is equal to m times A, okay? So if the net force acting on a system is different from 0, then we have m times A on the right side. But what happens if the mass changes? If the mass is not constant? Look at this example. On the right side, we have a rocket and it has certain mass. Let me write this one. At the beginning, we have a rocket. This is the payload, and this is the main body, and this is the engine, let's say, okay? So the mass of the payload, mass of the main body, okay? Mass of the motors and all other things. And also here we have fuel of the rocket, okay? Plus fuel, okay? We have many masses here. So what about the mass of the fuel? At the beginning, total mass of this system is given with m1, m2 plus m3 plus m fuel, let's consider. Whenever you fire this rocket, what happens? This m fuel decreases, okay, because fuel goes out. So the total mass of the rocket decreases. Then you cannot use this expression, okay? In this case, it is better to use momentum considerations instead of using this law. So A rocket is propelled forward by rearward ejection of burned fuel that initially was in the rocket. So eject the fuel, okay, in this direction, and then this produces a force in forward direction. You apply Newton's third law, okay? So the forward force on the rocket is the reaction to the backward force on the ejected material, ejected fuel, okay? The total mass of the system is constant, but mass of the rocket itself decreases as material is ejected. So at the beginning, we have this total mass, and whenever the rocket is fired, look at the level of the fuel here. It is full, and now half of the fuel is spent, and the fuel is here. Now we have dm, okay, some part of the fuel, and here mass is given with minus dm, you can consider, okay? So total mass of the system, if you look at this one, before starting the motors, we have certain mass, and after we fired the motors, then we have again total mass m, but some part of the mass is moving in this direction and some part of mass is moving in this direction, okay? So the total mass of the system is constant, but the mass of the rocket itself decreases as material ejected. So mass of this part decreases, okay? Now, let me continue step by step. A rocket burns fuel, its mass decreases. So here we have ejected fuel, okay? So mass of this one decreased. To provide enough thrust to lift its payload into space, this Atlas V launch vehicle ejects more than 1,000 kilograms of burned fuel per second at speeds of nearly 4,000 meters per second. Okay, so we will go into detail. So this is very nice application of rocket propulsion. So now let me continue. For simplicity, first of all, let's consider a rocket in outer space. Why we are considering a rocket in outer space? Because we don't want to deal with the gravity. We don't want to deal with the air resistance. Okay, actually, in this condition, there is a gravity, okay? And this rocket has certain weight, and there is also air resistance, okay? So you have to consider friction forces, air friction, and we have forward force produced by the ejected mass of the fuel, okay? So actually free body diagram is like this. The F thrust, and this is the weight, this is the air resistance, okay? F friction, you can say, or F drag, okay? So, but if you are talking about the rocket is moving in space, then you can consider there is no gravity, there is no air resistance, okay? We have just this F thrust, okay? For simplicity, we are considering this condition. Then M is the mass of the rocket, and this mass will change as it expends fuel. Here, this is the first condition. We are in space, we have a rocket in the space, and this rocket has certain velocity and certain mass when the time is t, okay? So, in the first condition, here, the momentum of the rocket is given with m times v, mass of the rocket and velocity of the rocket. in a short time interval dt, here in this case, when the time is t plus dt, what happens? The mass of the rocket changes by an amount of dm. Okay, now the mass, new mass is m plus dm. Don't forget this. This dm is negative because mass decreases. Okay, at the beginning, this mass was m, and now after dt times, the mass becomes mass plus dm, the change in the mass of the rocket. And what about the velocity? Velocity of the rocket during this dt times becomes velocity plus dv. Okay, now let's go into detail. So here we have a motor of the rocket, and fuel is exhausted from this motor with some certain velocity, and this velocity is called as exhaust speed of fuel relative to the rocket. Okay, this is the velocity of the rocket, and this is the V exhaust speed of fuel relative to the rocket. Be careful, we will define different velocities in this example. So the burned fuel here, this is the burned fuel, is ejected opposite to the direction of motion. This is the direction of the motion, let's say positive x. This is the direction of the ejected burned fuel. Okay, so its x component of velocity relative to the rocket is minus v exhaust. This is the exhaust speed of fuel relative to the rocket. Don't forget. And what about the x velocity of the fuel, of the burned fuel, relative to our coordinate system? Okay, you are watching this rocket from the ground, okay? Then what is the velocity of this burned fuel relative to our coordinate system? So the velocity of the burned fuel is equal to the velocity of the rocket plus the exhaust speed of the fuel relative to the rocket. And here we have a minus sign because it is opposite to the velocity of the rocket. Then here I have this one. This definition is very important. If you don't understand this definition, it is not necessary to continue. This is the relative velocity of the fuel to the observer in our coordinate system. And this is the velocity of the rocket. And this is the exhaust speed of the fuel relative to the rocket. Okay. Then what about the momentum of the ejected mass? So momentum of the ejected mass, what about the ejected mass? Ejected mass is given here. As I told you, dm is negative, okay? Mass is decreasing. So what about the mass here? The mass in the fuel, exhausted or ejected fuel, increases, okay? So since dm is negative, here I put negative, then in total I have positive. Is it clear? If this is not clear, please let me know. So what about the momentum? Momentum is given with m times v. So this is the mass of the fuel. This is the velocity of the fuel. Then just take this v fuel here, and then we have this expression. This is the momentum of this ejected fuel, okay? Then the x velocity of the rocket and unburned fuel. Within this rocket we have another fuel which is unburned, Okay, we will use this fuel later on, has increased to velocity plus dv. So velocity of the rocket and the fuel within the rocket, unburned fuel, is increased and its mass has decreased to mdm, m plus dm. And don't forget that dm is negative. Actually, we have a decreased mass in total within the rocket. So here we have momentum, let's say P1 when the time is t, and here we have momentum P2, let's say, when the time is t plus dt, okay, in the second case. So then what about the rocket's momentum at this time? Rocket's momentum is given with m plus dm, mass of the rocket, plus velocity of the rocket. Okay, this was the momentum of the rocket when the time is t, and this is the momentum of the rocket when the time is t plus dt. Mass is this one, velocity of this one. So the total x component of momentum P2 of the rocket plus ejected fuel at time t plus dt. So when the time is t plus dt, we have momentum of the rocket, we have momentum of the ejected fuel. Okay, you can remember that before this time we have fuel and rocket are together, okay, and then we have total momentum of the system is given with this expression. But after dt time, then we have this condition. Now we have momentum of the burnt fuel and we have momentum of the rocket with new velocity and new mass, okay? So then P2, the total momentum of the rocket plus ejected fuel at time t plus dt. What is this? This is the momentum of the rocket. This is the momentum of the fuel, which we have calculated. Then, if there is no net force acting on this one, if there is no net force acting on this rocket, we have considered that this rocket is traveling in space. There is no air resistance, there is no gravity, so external force is zero, then momentum is conserved. Okay, you can apply conservation of momentum, but don't forget this is special condition. So if momentum is conserved, then this P1 is equal to P2. P2 is this one, and P1 is this one. Okay, then mv, initial total momentum of the system, is equal to P2, final momentum of the system when the time is t plus dt. So what do you see here? mv, here you will have another mv, here you will have dmv. So all these multiplications will give you this result, this one here. mdv is equal to minus dm vx minus dm dv. Okay, so here we have a term, multiplication of dm dv. What was dm? The change in the mass of the rocket. dv is the change in the velocity of the rocket. So since these very small changes are very small quantities compared to these terms, then you can ignore this one for simplicity. Okay, then what we have here, if you divide these two sides of the equation, this dt, then you can get this expression. So what is dv over dt, or time derivative of velocity? What is this? This is acceleration, okay? And m times a, this is the force. And on the right side, what we have? Minus vx times dm over dt. What is dm over dt? This is the time derivative of the mass and shows us how the mass of the rocket changes by time, okay? So what about this force? This force is thrust. Force is F thrust, okay? And the thrust is proportional both to the relative speed Vx of the ejected fuel, this one, and to the mass of fuel ejected per unit time, this one, minus dm over dt. So look at this Vx. What is this one? The relative speed of the ejected fuel. So here we have a rocket and we have a motor, and this motor burns this fuel here and then eject it with some certain velocity. This is the Vx, okay? So if you have higher Vx, then you have higher thrust, okay? And what about this dm over dt, the change in the mass of the rocket? So this mass of the fuel is ejected by using this motor here, this engine here. So this motor is very strong, very effective to provide this huge dm over dt's. Then again, you will get very huge thrust, okay? So in order to get good rockets, effective rockets, both this relative speed of the ejected fuel and the change in the mass of the rocket must be huge, okay? Then you can provide huge thrust forces. So here we have A, look at this one. If I take this A, then I can get this expression. This is the acceleration of the rocket, okay? Acceleration of the rocket, very important formula. So this acceleration is positive. Here we have a negative sign, but the acceleration is positive. Why? Because what about this Vx? Vx is relative speed of ejected fuel. It is speed, okay? Then it is positive. I'm just talking about its speed, okay? Not velocity. So it is positive. So, and what about dm over dt? Dm over dt is negative because mass is decreasing by time. Since this is negative, and here I have another negative, then I have positive acceleration in total. So the rocket's mass m decreases continuously while the fuel is being consumed. So what do you see here? Look at this mass. Look at this mass. Mass decreases. Okay, mass is not constant. You see? Let me show you. Let's consider that this Vx is constant. You have a rocket and it provides a constant Vx, and this engine of the rocket also provides this constant dm over dt. So here I have two constants. Then I can write this expression like this. A is equal to constant over mass of the rocket. So what about mass? Mass of the rocket decreases by time, then A increases. So we have a non-constant acceleration because mass of the rocket decreases, okay? And we have acceleration, 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 okay? Then we can apply thrust force to the rocket, then it can reach at very high velocities. This is the summary. If Vx and dm over dt are constant for certain rocket engine, the acceleration increases until all the fuel is gone. So when the m is lost, total mass of the rocket is 0, then you don't have any thrust, okay? So now let me continue with this definition again. Acceleration of the rocket, we have minus Vx over m dm over dt, okay? So this equation here, this one tells us that an effective rocket burns fuel at a rapid rate, large dm over dt, and ejects the burned fuel at a high relative speed. So in order to produce good rockets, in order to produce good missile defense system, you have to consider these two important terms here, okay? Your motors, rocket engine should produce large Vx, and they should produce large minus dm over dt, then you can produce very fast, very powerful rockets, okay? So just consider that the exhaust speed Vx is constant, okay? Then what to do? Look at this equation. Here we have dv over dt is equal to minus Vx over m dm over dt. Okay, so take this one and this one, then here I have dv is equal to minus Vx times dm over dt. So just consider that this is constant, and velocity changes, mass changes. These are not constant. So take integral of this side, take integral of this side. Then the velocity from the initial velocity to the final velocity, this integral, minus Vx, you can take it out. Initial mass of the rocket, final mass of the rocket, dm prime over m prime, okay? Then if you solve this integral, then you will get this expression. This is the delta V, the change in the velocity of the rocket, which is equal to minus Vx ln m over m0, okay? Or you can write like this, Vx, here we have minus sign, here we have a plus sign, but look at this one, m over m0, here we have m0 over m, so you can write it like this. So now we have this expression, and let me introduce what is the meaning of this expression in rocket propulsion applications. This is the final transparency of this part. So here we have m0 over m, this in the ln, okay? The ratio m0 over m is the original mass divided by the mass after the fuel has been exhausted. At the beginning, the mass of the rocket is given with m0, and after certain time, the mass of the rocket is decreased to m. Okay, this is the ratio. In practical spacecraft, this ratio is made as large as possible to maximize the speed gain, which means that the initial mass of the rocket is almost all fuel. This is very nice information, very useful. So you would like to produce huge change in the velocity of the rocket. You would like to reach to the high speeds. In order to get very high speeds, then you should have very high exhaust velocity and you should have very high this term. So what is the meaning of them? You should have this type of relation. This must be huge, okay? What is the meaning of this? This is the initial mass of the rocket, and this is the final mass of the rocket, okay? So if the initial mass of the rocket is almost all fuel, then you can reach at very high speeds. So what I mean, actually, this payload has certain mass, and this engine has certain mass, okay? And this body has also certain mass. And here we have a fuel. Fuel has also certain mass. And this M0 is including all these masses, M1, M2 plus M3 plus M fuel, okay? If you can keep all these masses very small, and if you can get more or less this type of condition, so the total mass of the rocket is more or less equal to the mass of the fuel within the rocket, then you can provide very effective rockets. This is the definition of this equation. Then let me continue other physical results of this equation. Then let me finish this part. So the final velocity of the rocket will be greater in magnitude and is often much greater than the relative speed of Vx. What was Vx? Relative speed of the exhausted fuel relative to the rocket speed. Okay, we have assumed throughout this analysis that the rocket is in gravity-free outer space. We have considered that the rocket is moving in space. There is no gravity. We have ignored the air resistance. But in real applications, for example, for this case, you have to consider the gravity. You have to consider the air resistance, okay? I have also discussed this condition here, and I have shown the forces, thrust force in forward direction, weight in backward direction, and also air friction in backward direction. These are the acting forces on this rocket. Have any question with this part? If not, I will continue with these two examples. Acceleration of a rocket. The engine of a rocket in outer space, far from any planet, so you can consider gravity is zero, is turned on. The rocket ejects burned fuel at a constant rate. In the first second of firing, it ejects 1/120 of its initial mass of m0 at a relative speed of 2,400 meters per second. What is the rocket's initial acceleration? So what is the dm over dt, the change in the mass of the rocket, which is given with minus m0 over 120, which is given in the question, and it happens within 1 second. Okay, where is it? In the first second of fire. The time is 1 second. Okay, it ejects this mass. So it is dm is negative, minus m0 over 120 over dt is 1 second. Then I have dm over dt minus m0 over 120 seconds. So then what about the acceleration? This is the question. Acceleration is given with minus vx over m0, dm over dt. We have calculated dm over dt here. And then vx. What is Vx? This is the relative velocity, relative speed of the ejected fuel. It is given, okay? Then put it there. And what about the mass? M0, okay? Just put here M0. And then here we have M0, and here we have M0. This M0 will cancel this M0, and then you can find the acceleration of the rocket. Look at the acceleration. It is 20 meters per square second. Remember the G, gravity of the Earth. It is huge compared to the gravity, okay? So it is 20 meters per square second. And now let's have a look at the speed of a rocket. Suppose that 3 to 4 of the initial mass of the rocket in this example is fuel. So what do you see here? That 75% of the total mass of the rocket is fuel, so that the fuel is completely consumed at a constant rate in 90 seconds. The final mass of the rocket is M is given with M0 over 4. So 75% of the mass is exhausted. If the rocket starts from rest in our coordinate system, find its speed at the end of this time. So just apply this equation. Here we have found this relation between the velocity and the change in the mass, and also relative velocity of the exhausted fuel. Then here you can use V is equal to V0 plus Vx times ln m0m. So what is V0? The initial velocity is 0. Why? Because the rocket starts from rest. So it is 0. Vx is given in the question here, 2,400 meters per second. Put it there. And what is ln m0 over m? M0 over m is given here. Here we have ln 4. And this is the final velocity of the rocket after certain time, which is given with 3,327 meters per second. Then let me finish with this bio application. This is the jet propulsion in squids. Squid in Turkish mürekkep balığı. Both a jet engine and the squid use variations in their mass to provide propulsion. So they change their masses, okay? They increase their mass by taking in fluid at low speed. So a jet engine takes air into the engine, and then its mass increases. And here, these squids take water, okay, into their bodies at low speeds, so they increase their mass. Then they decrease their mass by ejecting that fluid at high speed. So at the beginning, at low speeds, they take water into their bodies, and then they eject this water with very high speed. Then they produce F thrust in the forward direction. This is the also mechanism in jet engines, okay? Let me draw. Let's consider this is a jet engine, okay? Jet engine of an airplane. And then air enters into the motor, okay? And also fuel enters into the motor, and they are ejected at very high speed. The exhaust is huge, okay? Then they can provide thrust. The Caribbean reef squid shown here can use jet propulsion to vault to a height of 2 meters above the water and fly a total distance of 10 meters, about 50 times its body length. As much as I remember, this is the water and this is the air, okay, and they can jump up to 2 meters height, and they can travel, let's say, 10 meter. This is the total distance. Okay, this is the bio application of jet propulsion in squids. Do you have any question related to the rocket propulsion? With this transparency, I finish my lecture. Take care of yourself and try to solve the problems and questions at the end of this chapter. Bye-bye.